Hi, pre-calculus. Here we are in section 5.2. We're looking at trigonometric ratios in right triangles. Hopefully much of our vocabulary seems like, or is rather, review. So we're going to just get started with the image of a right triangle and talk about its parts, because that's a lot of what we have going on in our first few vocabulary words. So when you have a right triangle, you know that there is an angle that is 90 degrees, and the side opposite that angle that is 90 degrees is referred to as the hypotenuse. And so I want you to keep that in mind. It's always the longest side. The other two sides are interchangeably referred to as the legs. So that's the legs of our right triangle. And sometimes, if you're going to go back to Pythagorean Theorem, one side is A, the other side is B, or one leg is A, the other leg is B, and the hypotenuse is always C, B and A being interchangeable. All right, so with that in mind, let's look at side adjacent and side opposite. So when we talk about trig, when we're dealing with trig, you may remember that we are, when we start off with right triangle trig, we're going to talk about some angle within the triangle. Let's call this one angle X. And then we are going to refer to the sides of the triangle in reference to the position of X. Now, the hypotenuse is always the hypotenuse. However, the sides can go by other names, all right? So the sides, depending on its location with X, might be referred to as the side adjacent to X. That would be that red line, because it's adjacent right next to the X angle. And the side opposite X would be the side opposite X. So we would call it this guy over here. Let me change the color real quick. So we would call it this side over here. So opposite is just across the street from the angle that I'm standing at. I often really talk about it like that, like just say I'm standing at this angle, because sometimes I could be standing at this angle and then that switches the whole thing around, because if I'm referring to this angle, call it Y, the side opposite Y is the red one as opposed to the purple one. You with me? So you really need to be aware of the angle with which you are, the reference angle that you're referring to when you consider these things. So we got through the first four trigonometric ratios. So you will remember that the ratios of these sides together are going to be referred to as sine, cosine, tangent. These are the three majors, and then cosecant, secant, and tangent, which are important as well, but a little bit less explored. So we're going to focus on these. So sine, if you remember, the abbreviation is that, is equal to the opposite side over the hypotenuse. And instead of writing it out, I'm actually going to abbreviate it even more and just do O over H, all right? So sine is equal to O over H. Cosine is equal to A over H. And then tangent, the tangent of angle X, right? Because again, we need to consider the position that we're standing at. The tangent of angle X will be the opposite over the adjacent. And so you may remember a mnemonic device to memorize this as SOH, CAH, TOA. And it is affectionately known as SOHCAHTOA. So sometimes when I have students who haven't memorized this or don't remember, I would say if you're taking a test, if you're working on anything with right triangle trig, just write down the mnemonic device SOHCAHTOA, and you will always have a way of thinking through the whole thing. All right, so now we get to these guys. These are also trigonometric ratios. Again, as I said, a little bit less used, and so not a real mnemonic device, but their relationship with the other ones are going to be necessary. So the cosecant, which abbreviated looks like this, the cosecant of X will be the reciprocal of the sine. So instead of O over H, it's going to be H over O. So sometimes you might even see 1 over sine of X being referred to in reference to the cosecant. It is the reciprocal. They're reciprocals of one another. The secant is going to be the reciprocal of the cosine. So that's going to be H over A. And of course, we can again write it as 1 over cosine X. And finally, the cotangent, which is right there. The cotangent, abbreviated COT, is going to be the reciprocal of the tangent A over O, which is 1 over the tangent of x. So hopefully that's pretty okay. Then we have this concept of cofunctions. So cofunctions basically are talking about the relationships between two functions that are or two ratios that are going to be equivalent when you're dealing with the complement. So if you remember from geometry, the complementary angles are two angles that add up to 90 degrees. And so if you think of the complement of, they're using this Greek letter theta and not x like we did. If you think of the sine of some angle theta, that's going to be the same as the cosine of 90 minus theta. Tangent of theta is going to be the same as the cotangent of 90 minus theta. So let's think about what that means. I'm going to do one quick kind of example, and I think it'll make sense after we just kind of do this. So here we have a right angle triangle, and let's say that this is 70 degrees, and if I'm down here at angle that is 70 degrees and I want to talk about the opposite and then the adjacent, and then let's do the hypotenuse in green. So if I want to talk about the ratio of these sides, watch this, the sine of 70 degrees will be this purple over green, right? It'll be purple over green. You see that? Purple over green, whatever that is. So I don't know, maybe I should just do purple over green, right? So then it's going to be purple over green, whatever that measurement is. So think about if we were to talk about the cosine of this angle up here. Now, if I'm up here, this is 70, this is 90, we know all of this adds up to 180. This right here has to be 20 degrees, which we know is 90 minus 70 is 20. What is the cosine? Cosine, again, if I scooch back up here, is adjacent over hypotenuse, which is adjacent to the 20 degrees is purple over green. Are you with me? So that will be the same as the cosine of 20 degrees. And so that's why we see this relationship that they're discussing, and we'll see similarly these relationships happen with the cotangent, cosecant, and the tangent. All right? Okay, cool. So with that in mind, let's take a look at some problems. In example 1, we're going to find the values of the sine, cosine, and tangent for angle B. So here is where I am standing. This is my angle of reference. Let's keep in mind that the hypotenuse is always going to be across from the 90-degree angle. And I should have written that this is indeed a 90-degree angle. And so now that we've got that, let's think about what we know. We know that we've got SOHCAHTOA, which is going to give us some information as to how to find the sine of angle B. So the sine of angle B is going to be equal to opposite over hypotenuse, so 18 over 33. I can reduce that. And when I do, I get 6 over 11. So 6/11 is the ratio that refers to the sine of angle B. Let's go for the cosine of angle B. So the cosine of angle B, remember cosine is adjacent over hypotenuse. So I know that the 33 is going to be in the denominator, but this adjacent one I need to figure out. And the way I'm going to do that is the Pythagorean Theorem. So you remember we kind of briefly mentioned it earlier that the Pythagorean Theorem is going to have that the legs of the right triangle are interchangeably A and B, but the hypotenuse is C. And so with that, we're going to apply the formula a squared plus b squared equals c squared in order to find, in this case, b, so we can figure out the cosine of angle B, lowercase b, so we can figure out the cosine of capital B. I also named this pretty poorly, but whatever. Yeah, this is C. Since this is A, we should name this one A. That's just a convention in geometry, but I'm going to ignore it for now. You guys know what I'm talking about. All right, so then A squared, in this case, is 18 squared plus b squared, which we're not sure of, is equal to 33 squared. So I know that b squared is going to be equal to 33 squared minus 18 squared. And then to find b, I'm going to just take the square root of all of that. So to find side b, I'm going to take the square root of 33 squared minus 18 squared, which gives me the square root of 765, and then we can simplify that to the exact answer of the square root of 3 times the square root of 85. And so we're going to now take that information and plop it up here because that's this length, and we know that, again, the cosine is going to be adjacent over hypotenuse. So we've got 3 times the square root of of 85. And to reduce that, I guess we could do square root of 85 over 11. So that's going to be the ratio that is associated with the cosine of b. Let's go ahead and find out the tangent of b. So the tangent of b is going to be equal to opposite over adjacent. The opposite is 18. The adjacent we calculated as 3 over the square root of 85. And so we can go with that. This is a ratio. Mathematicians have historically been against leaving radicals in the denominator because it doesn't make for easy computing, and it's kind of weird to talk about 18/3 root of 85. So that's a little weird. So we're going to first simplify, and when we do that, we get 6 over the square root of 85, and then we'll rationalize the denominator by multiplying top and bottom by the square root of 85. You with me, guys? You remember this. Then we get 6 root 85 over 85. And that is the sine, cosine, and tangent of angle B. So here in example 2, we're going to be talking about the example from the beginning of the chapter. We see that we are dealing with this concept called Snell's law, which is that the sine of the angle of incidence over the sine of the angle of refraction is equal to some constant n, where the sine represents a trigonometric ratio and n is a constant called the index of refraction. So here we have light coming in, shining through the air at a particular angle, and that is the angle of incidence, and then we have the angle of refraction as it comes through as it shines through glass. And so what we're going to do, the angle of incidence, we're going to figure out the index of refraction, which is n. The angle of incidence is 50 degrees. The angle of refraction is given as 32 degrees and 16 minutes. What we're supposed to do is calculate this value. So how can we do it? Well, we can do pretty easily the sine of 50 degrees. We can grab a calculator and do that. The sine of 32 degrees and 16 minutes will be a little bit more challenging on most calculators. Maybe there's a calculator that does it, but what I want us to do is to change 32 degrees and 16 minutes into a complete decimal version of the degree. So we know we're going to have 32. We're going to add to 32 16 over 60. Does that make sense? Because we know that 60 minutes is going to give us a degree. Therefore, 16/60th of a minute is what we have here. Then we're going to add that on. And when we add that, let me grab a calculator real quick. All right, so we get 32.26 repeating degrees. And so for us, we're going to now just use our calculator, take the sine of 50 degrees, divide that by the sine of 32.26 degrees. And 26 repeating degrees, and we'll get the incidence or the index of refraction. Want you to make sure that your calculator is not in radians though, because that's a different degree measure. So make sure your calculator is in degree, especially if you're doing this with me, and then you will divide both of these values and we'll find out that the index of refraction is approximately 1.434915, something like that. And that's going to be our answer. All right. Here in example 3, I would suggest us just drawing a picture just to represent the situation so we could find the secant and find the cosine. But if you also, well, cosine in this situation, but you might also remember the relationship. You remember earlier we said that the relationship between cosine and secant is that the secant and the cosine are reciprocals of one another. And similarly, the cosecant and the sine are reciprocals of one another. So as we do this problem, I'm going to write out what we should know. So we know that the cosine, in this case anyway, the cosine is equal to 3 over 4. Cosine, I like to write this all the time. The cosine being the opposite over hypotenuse tells me that I could represent this with a situation where if theta is here, the opposite, oh no, not opposite, adjacent over hypotenuse. The adjacent is 3. Thank you guys, don't be mad at me. Is 3 and the hypotenuse is going to be 4. And then we remember that the secant is going to be the inverse. It's going to be hypotenuse over the adjacent. So the secant of theta in this case will be 4 over 3, the hypotenuse over the adjacent side. Or I could have really just said the reciprocal of this, and we'll do that in this case. So if the cosecant of theta is 1.345, and I'm not going to draw a triangle such that that's the case, find the sine. So really what I'm looking for is the reciprocal of this situation. So with that, we get that the sine of theta is equal to the reciprocal, which is 1 over 1.345. And that approximately is going to be, with the help of a calculator, about 0.744. Our final example requires us to find the values of the 6 trigonometric ratios, and we're standing at angle P. The first thing we should do is to find the length of the hypotenuse, which is going to require a little bit of Pythagorean theorem, which we're pretty familiar with. So we've got 100, that's a squared, plus 49 is equal to c squared. So c is equal to the square root of 149. And I'm just going to hold on to that right there because I'm not sure if we could simplify it. I don't think of there's a perfect square that divides evenly into that, so we're just going to go with it. So if I have to do the sine, I like to do the first 3 because I keep them in mind all the time, right? So if I know SOHCAHTOA, I can start off with that and then just do reciprocals to find the other less used 3. So the sine of angle P is going to be equal to opposite 7 over the square root of 149. And the cosine of angle P is going to be equal to, write that there, is going to be equal to the adjacent over the square root of 149. And then the tangent finally is going to be equal to 7 over 10, which is opposite over adjacent, right? And then so we know that cosecant is the reciprocal of sine. Therefore, the cosecant of P is going to be the square root of 149 over sine. The secant of P is going to be square root of 149 over 10. And then finally, the cotangent of P is going to be 10 over 7. All right, that's our last example. I hope it made sense. Let me know if there's some things that I can straighten out for you guys, and I'll talk to you soon. Take care.